And today we are starting off the program with Dr. Jessica Shade, who is live from California, where she says it's raining. And we were just saying, yay, that's a good thing for California. She is the director of the science program at the Organic Center, where she directs projects associated with conducting research in organic agriculture. And she has been with the Organic Center for quite a long time. She's got excellent research that she's going to be presenting today on the topic of organic and climate change. She has been honored for her environmental accomplishments by the Audubon Women in Conservation through their Women Greening Food Special Recognition, and the Ecological Society of America Student Section and Union of Concerned Citizens through their Eco-Service Award, and is a Schweitzer Environmental Fellow. She received her PhD from the University of California in Berkeley. So we'd like to welcome you, Dr. Jessica Shade, and over to you to start sharing your slides.
Great, thank you so much, Tia. And while I'm pulling up my slides, I'll share a little story. Tia mentioned that it is raining here, which is great. And, you know, I actually grew up in California. So the fires that we've been experiencing from climate change are new to me, at least new that they happen every single year. And it didn't really hit home how annual the devastating fires are here until I was talking. I have a 3-year-old son, and I was teaching him the months. So we were going through all the months, and we got to August, and he looked at me and said, August means smoke. And it just kind of blew me away, where I was like, oh yeah, in your lifetime, every August, the air is just choked with smoke almost all month. So it's kind of, that happened recently, and I thought I'd share because it is a little window into how climate change is accelerating and happening now. And I feel like just a few years ago, when we talked about climate change, it was this esoteric idea of what things could happen in the future. And now it's here now. So I'll go ahead and get started. As Tia mentioned, my name is Jessica Shade. I'm the Director of Science Programs at the Organic Center. And today I'm going to be talking about the role that organic agriculture can play in mitigating climate change and how it can also be part of the solution. So first, I'll talk about why we should even consider organic agriculture when we're talking about climate change. So we all know that driving cars and industrial factories are important, but why is agriculture so important? And also, for those of you who are farming or making changes in your supply chains for your final products, why should you consider the way that your sources are produced? And then I'm going to dig into the science to look at the facts that have been published about organic agriculture when it comes to climate change mitigation, including actual data from peer-reviewed studies. So get ready to see some graphs. So a huge chunk of the world is covered with farms. When you look at the ice-free parts of the world, about 40% is used from agriculture. And so this is a map, so you can really visualize what I mean when I say that a huge percentage of the world is used for agriculture. Everything that you see in brown on this map is range and cropland. And basically, other than the areas that are covered in ice, deserts like the Sahara, rainforests like the Congo and Amazon, basically everything else is used for agriculture. And the global population is expected to exceed 9 billion by 2050. So the extent of our success in mitigating climate change is really going to be tied to sustainably managing agricultural land that's already under production. And a lot of people don't think about agriculture as being a major contributor to total greenhouse gas emissions, but research on this shows that food systems as a whole contribute 19 to 29% of human-caused greenhouse gas emissions. And of those food emissions, about 80 to 86% is from agricultural production specifically. And those greenhouse gas emissions contribute directly to climate change, and the projected increases in extreme weather events have a real potential to threaten our food safety, not to mention the security of our food systems. And as I mentioned, this isn't some esoteric idea for the future, so I would even argue that they already are contributing. So when it comes to agriculture and climate change, there are two ways to be a part of the problem or two ways to be a part of the solution. You can kind of look at it either way. So the first is by increasing or decreasing greenhouse gas emissions. And then the second is by releasing or sequestering carbon in the soil. So let's start by looking at greenhouse gas emissions. Greenhouse gases can be classified as direct emissions or indirect emissions. Direct emissions are greenhouse gases that are released on the farm. So things like burning fossil fuels by farm equipment, methane release from livestock and livestock waste, and nitrous oxide release from the breakdown of animal wastes or excessive nitrogen application. What indirect emissions are talking about are greenhouse gases that are released off the farm. And one of the biggest indirect sources of greenhouse gas emissions is fossil fuel use for manufacturing and transporting on-farm inputs, especially synthetic ammonium nitrate fertilizer, because the industrial factory process used to make that fertilizer, the Haber-Bosch process, needs a source of hydrogen atoms. And that source is typically natural gas or methane. So it's not just that it uses a lot of energy to operate a fertilizer manufacturing plant, which it does, but it's also that the actual chemical reaction used to make fertilizer requires fossil fuel inputs. Okay, so now let's look at some hard numbers for emissions. So these results are from a study that analyzes the environmental impact of the complete supply chain for producing a conventional loaf of bread. So this isn't an organic specific study. This is really just looking at what are the environmental impacts of producing conventional loaf of bread. So what they found was that more than half of the total environmental impacts occurred during wheat cultivation, and that the use of ammonium nitrate fertilizer on wheat crops was responsible for the majority of that environmental impact. Synthetic nitrogen fertilizer alone accounted for 43% of the total environmental impact of creating a loaf of bread. So when you're looking at this graph, we're going to focus on the second bar, the global warming potential. The other bars account for other environmental aspects, and I left them on there because you can see that synthetic nitrogen has a large impact outside of climate change. But for this presentation, we're going to focus on the bar with the big arrow pointing to it. And each of the different colors represents a different activity that occurs in the process of making a loaf of bread. Everything from preparing soil and planting seeds up to slicing and packaging the bread. And all of the colored bars within the bracket, those represent activities that are part of growing the wheat on the farm. And the red bar is the contribution of synthetic nitrogen fertilizer to the global warming potential. The large environmental impacts of fertilizer in this study was mostly driven by the carbon dioxide emissions from manufacturing synthetic fertilizer, as well as the release of greenhouse gas, especially nitrous oxide that happens from the breakdown of excess nitrogen fertilizer on the soil. So, again, nothing in this study focused on organic, but organic operations are prohibited from using synthetic fertilizer. So they're eliminating a big chunk of the production that has a huge environmental impact. So now we're going to look at energy use. This study used a life cycle assessment to model potential reductions in cumulative energy demand and global warming potential if Canada were to transition all of their canola, corn, soy, and wheat from conventional to organic. And the graphs show the amount of energy on the vertical axis. And the way I set it up on the horizontal axis is that all of the bars that are filled blue are conventional, and all of the bars that are filled green are organic, and the outlines correspond to the crop. So the first bar is the energy demand for conventional canola. The second bar is energy demand for organic canola. And then that's followed by conventional corn and then organic corn, conventional soy, organic soy, conventional wheat, organic wheat. And what the results show is that by completely transitioning to organic, crop production would consume an average of 60% less energy than conventional production. And they also looked at specific aspects of climate change and found that by transitioning to organic, they could generate 25% fewer global warming emissions and 80% fewer ozone depleting emissions, which resulted in a much lower level of global warming potential for each of those crops under organic cultivation. So this graph is similar to the last one, but instead of energy use, the vertical axis is carbon dioxide release, and then you can see it's consistently lower for the organic crops. And those differences between organic and conventional were almost exclusively due to different soil fertility treatments used in organic and conventional farming. And they were really driven by fossil fuel use in creating synthetic fertilizer and the emissions from their production.
Yeah, I got to give a Zoom presentation later.
So we talked about greenhouse gas emissions. Now we're going to flip that coin to talk a little bit about carbon. So right now, 80% of the world's terrestrial carbon is stored in soils. And with the exception of oceans, soils are the Earth's largest carbon sink. Now, with proper management of soils, we can increase carbon sequestration and contribute to climate change mitigation. But if we don't manage soils well, that can deplete carbon stores, releasing that carbon into the atmosphere and contributing to climate change. And that worst case scenario is exactly what's happening, according to a recent study. So these are results of a study that came out a couple years ago and was published in the Proceedings of the National Academy of Sciences. And what they found was that over the last 1,200 years, 133 billion metric tons of carbon have been lost worldwide in the top 2 meters of soil alone. And they also found that the rate of carbon loss has been increasing dramatically over the last 200 years. And that accelerated rate of loss is probably because of increased conversion of native ecosystems to agricultural land as our population increases and expands, and also because of intensification of how we farm. So if you take a look at this map, you'll see that a lot of it looks a lot like the one that I just showed you, except it's much more colorful. And basically any area that's yellow, orange, or red indicates soil carbon loss. And the areas that are orange and red specifically indicate the highest level of carbon loss. Now, the blue and green areas indicate places where there's been some soil carbon gain, but on the whole, you can see the map is dominated by yellow, orange, and red. And if you look at especially the United States, you can see this big area of red in the middle where it used to be native prairie, which stored a lot of carbon below ground, and now it's been converted almost exclusively to intensive conventional corn and soy production. So today's large-scale conventional farms are depleting our soils and contributing to climate change in several different ways. Some of the most harmful practices are the overuse of synthetic fertilizer and pesticides while recycling really little organic matter back into the soils. And you'll start to pick up on a theme as I go through these slides, which is that synthetic nitrogen that's used in conventional production has a big impact on climate change. So now for the good news, there's a growing body of research that points to organic farming techniques as a way to build soil carbon while reducing greenhouse gas emissions and improving energy efficiency. So things like fallowing, which allows organic matter to accumulate and decompose and restores nutrients to the soil, the use of crop rotations, using manure and legumes for fertilizer, which is especially important because using those alternatives aren't just replacing synthetic fertilizers, they're also putting organic matter back into the soil. So it's a double benefit. And then there's the prohibition of most synthetic pesticides, which are really energy intensive to create. And you know, one of the things that I hear a lot is that there's so much variation in techniques that are used within conventional and within organic management that you can't make a generalization on one system or another. But the Organic Center actually looked at this. So we took all of that variation into account. We collaborated with the National Soil Project at Northeastern University to take this huge snapshot to see exactly what's going on in organic and conventional soils from around the United States, so that we could really see the real world implications of all the management styles within organic and conventional agriculture and what they're having on soil carbon sequestration. And what we found was that even with all of those differences within organic and conventional, with all of the noise of different strategies on different soils, organic soils still had dramatically higher levels of long-term carbon storage reserves. And when I say dramatically, I also mean statistically significant, which was kind of cool because we had all of that noise that we accounted for in the statistical modeling. And we didn't just look at the total carbon in the soils, we were able to actually look at the different parts of the carbon. So we could see the carbon that fluctuates from year to year, and then the truly sequestered carbon that's locked away in reserves that won't be released for decades or even centuries. And our study wasn't alone. So these results are from a study that was conducted by researchers at the University of Illinois, who compared soil health among 9 long-term farming trial systems set up across the United States. And they were comparing 3 types of plots in each of those 9 locations: organic plots that use a combination of manure and legumes to increase soil fertility, organic plots that use only legumes to put nutrients back into the soil, and then conventional plots. And I just wanted to note that tillage was used in all of these plots. So when you look at this graph on the vertical axis, that's the amount of soil organic carbon, so the amount of carbon that's in the soil. And then the 2 green bars are from the organic plots. So the first bar, the light green one, represents the amount of, the first one, sorry, represents the amount of carbon that's from the organic plots that use both manure and legumes. And then the second one, which is actually looking orange on this graph, is just plots that use legumes. And then the last bar, which is blue, represents the carbon in conventional plots. So what they found was that when they compared the 2 types of organic plots, the ones that used just manure, the ones that use manure and legumes versus the ones that use just legumes, they didn't find any statistical significant differences in soil carbon. But when they, and so we put the letter A to show that they're the same statistically, but when they compare them to the conventional plot, they found that the organic plots had an average of 14% higher levels of soil organic carbon compared to the conventional. And the conventional was significantly lower than either of the 2 organic plots. So to represent that statistical difference in this graph, there's a B over the conventional plots. So for those of you who have really dug into the soil issue, you might be thinking, okay, you know, that's true in systems that use tillage, but everyone knows that conventional farmers use low or no till while organic uses full tillage. So what about that? So first of all, that's actually a big myth. According to the USDA National Agricultural Statistics Service, organic and conventional agriculture use conservation tillage practices about the same amount of time, around 40%. So that common refrain that you hear that all organic farmers till and most conventional don't is actually a fallacy. But, you know, let's play to the critics. Let's look at what happens when you compare soil organic carbon in organic full till to conventional no till. And this data is from the USDA's Agricultural Research Service from their Farming Systems Project. And this experiment was established back in 1996. So it provides a long-term comparison of organic to conventional cropping systems. And these graphs are comparing soil organic carbon between organic plots that do use tillage to conventional no-till plots. And just a real quick primer, conventional no-till usually uses the herbicide Roundup to control weeds in place of tillage. And proponents think that by reducing tillage, you're able to conserve more carbon in the soil because it protects it from losses that can occur when the soil gets tilled up and exposed to air. So typically studies that compare soil organic carbon sample at very shallow levels of the soil. But this study was a little different because it looked at carbon in the soil at intervals all the way down to a depth of 1 meter. So if we look at the first graph over on the left, the vertical axis is the soil depth. So at the top, 0, that's ground level. And then as we go down through the soil all the way to a depth of 80 centimeters. And then the horizontal axis is the total soil carbon. So each of the points represents a measure of soil organic carbon at different depths in the soil. And the dotted line with the round blue dots are measurements that were taken from the conventional no-till plots. And then the solid line with the green triangles are measurements that were taken from the organic full-till plots. And what you can see is that in the first 4 to 5 centimeters of soil, the conventional no-till plots do have higher levels of soil organic carbon than the organic full-till plots. But after about 6 centimeters, we see that trend reverse. And now the organic plots have more carbon all the way down to about 40 centimeters, after which point there's the same level of carbon. And on the graph on the right-hand side, the vertical axis is the amount of soil carbon, and the bars show the sum of the total soil carbon in each system, the blue conventional no-till, and then the green organic tillage system over the full depth of a meter. And what the results found was that soil carbon is significantly greater in organic plots than conventional, even when you compare full tillage in the organic to no-till in conventional. And that's because carbon in a no-till system mostly accumulates on the surface where those plant residues are deposited. But in an organic tillage system, those residues are worked down and buried into the soil. So there's greater soil carbon at deeper depths where it's more resilient to degradation. And the point of this slide isn't to suggest that we shouldn't be promoting reduced tillage for soil conservation. Really, it's just saying that the suite of soil fertility management practices used by organic farmers in combination with tillage still leads to greater increases in soil organic carbon than no-till conventional. So one last topic that I'll touch on really briefly before we have to leave the science part of this webinar is the resilience of organic systems to the consequences of climate change. Because organic techniques build soil health, organic systems can be better able to cope with extreme weather events. Things like drought and flood. Organic also relies on tools that are more flexible to abiotic and biotic stresses and fluctuations by maintaining a healthy, functioning ecosystem. And this has been shown in research, even in systems where organic typically has lower yields than conventional. In extreme weather years, organic outperforms conventional systems. So organic isn't only a model for how organic agriculture can help mitigate climate change, it also provides an opportunity for farmers to adapt to climate changes that we're already experiencing and that we'll continue to experience on an even greater scale. So if anyone fell asleep for that deep dive into the science that I was dragging you through, you can zone back in now because this is the punchline. So in summary, there is a lot of evidence out there showing the benefits of organic to both reducing greenhouse gas release and mitigating climate change by pulling carbon out of the environment into soil storage. But one of my favorite parts of the organic community is that we're constantly preemptively moving to improve the beneficial impacts that we have. So as more research comes out, which is happening as we speak, organic is going to continue to be the leader in pathways towards agricultural sustainability. So thanks everyone. And Tia, I think we're